Okay, in this video I just want to solve a couple more problems involving acid-base chemistry and buffer solutions. So let's get right into it. So the first problem I have here says, what is the pH of the solution when 0.001 moles of HCl is added to make a 1 liter solution? So first thing to notice is that this is HCl, which is a strong acid. It's hydrochloric acid. And that means it fully disassociates to H plus and Cl minus in solution. So all you really have to do with this problem is say that the pH is equal to the negative log of the concentration of HCl. So once you do this, you'll find out that the pH, plug this into a calculator or however you want to do it, that the pH is equal to 3. So that's pretty much the most basic pH problem you can possibly get. It's a strong acid making a 1 liter solution. So the second problem I have here says, what is the pH of a solution if 0.001 moles of sodium hydroxide is added to make 1 liter of solution? So this is pretty much the same thing here, only now we're dealing with a strong base. So in the case of a strong base, the first thing you want to do is recall another equation that says Kw is equal to the hydronium ion concentration times the hydroxide concentration. And that's called the equilibrium constant for water. Now with this we can use the concentration of sodium hydroxide and we can solve it for H3O plus, or hydronium ion concentration. And then that can simply be plugged in to the pH is equal to the negative log of H3O plus. So Kw is equal to 10 to the negative 14. So if we solve this equation for H3O plus, we find that Kw over the concentration of hydroxide is equal to the hydronium ion concentration. So all we got to do from there is just plug the numbers in. So 10 to the negative 14 over 0.001 moles, and that is equal to H3O plus. So if you plug that into your calculator, you'll find that the concentration of H3O plus is equal to 1 times 10 to the negative 11. So once you have that, you can just plug that into this equation over here, and that's exactly what I'm going to do. So the pH is equal to the negative log of 1 times 10 to the negative 11. So the pH for this 1 liter solution is 11. So again, a fairly simple problem, similar to the first one, but maybe just a bit more difficult. So the third problem I have here says the pH of blood is buffered by several mechanisms to maintain a value close to 7.4. Calculate the ratio of HPO4 2 minus over H2PO4 minus that is needed to produce a buffer at pH 7.4. So let's just start out with, we're making a buffer here, so we know we're probably going to be using the Henderson-Hasselbach equation. So we could say the pH is equal to the pKa plus the log of A minus over HA. So deprotonated over protonated versions. Now we don't have the pKa, but we are given the Ka in the problem, so we can solve for pKa by saying the pKa is equal to the negative log of the Ka. So pKa is equal to the negative log of 6.2 times 10 to the negative 8. So the pKa is equal to 7.2. So now that we have that, we can plug in a couple numbers here. So we'll start working with the Henderson-Hasselbach equation. So 7.4 is our pH, is equal to 7.2 plus the log of A minus over HA. So we can subtract 7.2 from 7.4, which gives us 0.2, and that's equal to the log of A minus over HA. So now we need to take the inverse log of both sides. So 10 to the 0.2 is equal to and what that winds up being is about 1.58. So 1.58 is equal to the ratio of deprotonated over protonated. So now that we have that, we need to do a little bit more algebra, and we need to say that HA plus A minus is equal to 100, because the ratio of protonated and deprotonated is going to be equal to 100. So simply solve for one of them. A minus is equal to 100 minus HA. Now we can plug that in to this equation over here. So what we can say is 1.58 is equal to 100 minus HA, and that's all over HA. So a little bit more algebra, we'll multiply 8 by HA, and we'll get 1.58 HA is equal to 100 minus HA. So we'll add HA to both sides. That gives us 2.58 HA is equal to 100. And then HA is equal to 100 divided by 2.58. So that means the concentration of the protonated form is equal to about 38.76%. So about 38.76% is going to be protonated. So to find out the ratio of deprotonated, we'll simply say A minus is equal to 100 minus 38.76, and that means that we're left with 61.24% of deprotonated. So the ratio is we wind up with 38.76% of protonated and 61.24% of deprotonated. And that makes sense because if you just look at where we were at, we're at a higher pH than the pKa. So that means we're going to have more deprotonated forms than protonated. So that's all I want to say for this video. Thanks.